right, so we can level this up slightly by not having the polynomial be factored ahead of time. Obviously, this doesn't add too much in terms of the difficulty, um, but we could go a little bit further. We could even say, well, what if it didn't have 0 on the other side? What if we had something like x cubed minus x squared minus 14x is, let's do greater than or equal to negative 24. So if we had something like that, well, it's still the same idea, right? Now this is much more complicated because we're not just dealing with a quadratic, um, but we also have some other pieces we've got to do. It's not factored, it's not set equal to 0 on one side. So I mean, it's not like any of that stuff is hard to fix. We could add our 24 to the other side. Bloop. And in fact, I'm going to show you two different ways to deal with this in just a hot second. Let me write this down and then I'll show you the ways we could deal with this in terms of using Desmos. So we got our plus 24. So this is not an easy, particularly polynomial to factor because it doesn't work in terms of factoring by grouping. But I will tell you what the factored version of this is. We know how to do all of this finding zeros. We've suffered through it. And in reality, hopefully we recognize that we would just use Desmos to look at the zeros. So we get this out as our solution. Oop, it's gonna pause because it's glitching. And we're back. All right. So again, I just want to show you that I like to set, like, I'm going to show you how to do it with and without setting a side equal to 0. But when a side is equal to 0, this is super helpful because now we can think about all of the information we have about graphing polynomial functions to just take this and go, okay, all right. We know the end behavior of a polynomial. By the way, we never did this problem because it was super boring. We know the end behavior of a polynomial with odd degree and a positive leading coefficient. It's going to do this. We now also know its zeros. It's got a 0 over at 3, a 0 at 2, a 0 at negative 4. And each of these zeros have multiplicity of 1, so they all have odd multiplicity we're going to cross. So we can sketch out this graph connecting all those pieces. Ooh, I'm going to do a better job of connecting them. And if I really wanted to, I could also throw in that y-intercept. It doesn't matter. The only thing I need for the inequalities are the zeros and that end behavior. But I could go ahead. This has got to go here, through, back up, through. Whoop. All right, I connected everything with a smooth, continuous curve, which we know we have to have for polynomial. And then we go back to the drawing board and we go, okay, well, what did we need? We needed it to be greater than 0, which means above the x-axis. So we care about this section and we care about all this section. And so what does that translate to in terms of our intervals of x? Because we know this is all about when does it happen, which is about the x's. So the x's between here and here, and then from here on. And translating that to interval notation, we have an equal to, so we do have hard brackets. What is that? Negative 4 up to that 2, or 3 off to infinity. So there's our solution, right? We could, of course, make our table if we wanted to, that little interval. We could do that sign test. We know negative 4, 2, and 3 are our options. The nice thing is, too, if I don't want to draw out the whole curve, I don't have to draw out the whole curve. I know these are all filled circles because they're solutions. I know the end behavior of a polynomial with degree 3. I know that this is going to be positive, so this is all a solution. I know we're crossing, so it's going to be negative. We cross again, so we're positive, and we cross one last time to get our end behavior that's negative. So again, you can jump straight to this and just use end behavior and multiplicity of your zeros to fill in this whole table without making an entire sign chart or actually plugging in values. So hopefully that shows you how awesome this can be. I did want to show you, I remember now that I was talking about it, I do want to show you guys the Desmos graph, both before and after I set aside equal to 0, because I do think that that's an important idea to look at. So let me bring this over and take up half the screen. So we need our x cubed. Remember, if we're going to use this as is, we just type in both of these equations. Oops, x squared minus 14x. And then, so that's my first equation. That's my first y equals. The second y equals would be the negative 24. I guess I should put y equals. It's not going to be mad. It's going to be mad at me otherwise. So we could take this graph, we could scroll over, we could see negative 24. We could click here, negative 4, 2, negative 4, 2, and 3. That's exactly where our zeros were. Right, let me actually make that go away. So we got our negative 4, our 2, and our 3. And remember, this is all about direction. So the fact that we have this greater than, that's telling me that I want the polynomial to be above the constant line, that horizontal line. So where is it above? Oh, it's above here, right? It's above here, and it's above here. So I can still get the same thing without doing that set aside equal to 0. I do think in many cases it's easier to just have the side equal to 0. So I could do that. This is a plus 24 because it's just easier to look at the graph and see the zeros and see above. Again, it brings it back to the stuff we've been doing in the previous sections to set aside equal to 0. But it's not necessary. You just treat these two things as two separate functions and see when one function is above the other in terms of y, when the outputs are bigger than the outputs of the other function. So that's it. That is solving a much, much more complicated polynomial. That's as complicated as it gets. We had a side not set equal to 0. We had the need to factor something that wasn't easy to factor. Definitely not easy to factor. This is one where you would have had to use all of our skills from 3.6 or just Desmos to get to the answers. Um, the only other way that I think is more complicated is, and I don't even have one in the Lumen book or the other book that's up, but you see it sometimes in, I think the Bittinger book for 96 had it, where you can get something where some real jerky person does something like an x plus 3. This is not going to work, so don't actually do this problem, is less than like 5. So you actually have to do multiply out, then set aside equal to 0, and then factor again. So like that adds one more step. But again, that's just adding complexity for complexity's sake, and it doesn't really make the problem any more meaningful or exciting. But yeah, that is solving a polynomial inequality.